Welcome back to JEE Maths Unlocked. Here's your problem of the day, and it's got a twist of geometry and probability. Imagine a perfectly equilateral triangle. Now, pick a point randomly inside it. Here's the challenge. What's the probability that this point lies closer to the centroid than to any of its sides? Sounds simple? Not quite. This problem connects ideas from locus, parabolas, and some elegant symmetry. Let's solve this problem. Think of a parabola, the beautiful curve traced by a point that stays equidistant from a fixed point called the focus, and a line known as the directrix. Now, take a step further. Can you picture the region where the distance from the moving point to the focus is less than its distance to the directrix? That's right, it's the region inside the parabola. Now here's where it gets truly elegant. Let's take an equilateral triangle. Locate its centroid, and imagine it as the focus. Now treat each of the triangle's sides as a directrix. Draw the three parabolas using this rule. What do you see? A beautifully bounded region formed by the intersection of three parabolic arcs. This is the magical space where a point is closer to the centroid than to any of the sides. And that is the exact region we're interested in. So now the question becomes, what's the probability that a point chosen randomly inside the triangle falls within this elegant zone? Stay with us as we reveal the answer, and yes, it's a simple, surprising fraction. Now this problem takes us into the world of geometric probability, where areas take the place of outcomes, and symmetry hides the solution. Now here's how we approach it. The idea is simple, yet elegant. First, identify the region. Let's call it region R, where a point is closer to the centroid than to any of the three sides. Next, we compute the probability as area of region R divided area of the triangle. But here's the twist. Region R isn't bounded by straight lines. It's enclosed by three curved arcs, each a parabola. This is where coordinate geometry meets calculus. Now let's take a closer look at the bounded region R, the beautifully curved area formed by the three parabolas. Here's the key observation. This region is perfectly symmetric. So we can divide it into three equal parts. Let's focus on just one of these parts. We'll find the area of this single segment, and then simply multiply by 3 to get the total. Now comes the smart move. Let's reflect this curved slice onto the coordinate plane, so that it aligns with a standard parabola, like y squared equals 4ax. With this, the region becomes easier to handle. And to make it even simpler, we divide this region into two halves, top and bottom, thanks to the symmetry of the parabola. So now, we just need to find the area under one curve, and double it. But how do we calculate this area? This is where the magic of calculus comes in. We apply the concept of area under a curve, integrating with respect to y, from the vertex of the parabola to the point where it intersects the boundary. To compute the area under the parabola and line GD, we'll integrate using a horizontal strip, so we need to know the limits of integration. Specifically, we need the y-coordinate of point D, the point where the parabola meets the bounding line of the region. To find that, we first need the equation of the line GD, which connects the focus of the parabola, our centroid, to the boundary of the region. Let's find the slope of this line. Since the triangle is equilateral, the angle between the medians is 120 degrees. So the angle GD making from positive side of x-axis is 120 degrees. So the slope of GD is tan of 120 degree, which is equal to minus root 3. Now apply the point slope form of a line. The coordinates of the focus, the centroid, is a, 0. So the equation of line GD becomes this. Now, recall that the equation of our parabola is y squared equals 4ax. To find the point of intersection, point D, we solve these two equations together. Substitute the value of x from parabola into the equation of line. Solving further, the y-coordinate of point D is 2a divided by root 3. Now that we have our limits of integration, it's time to calculate the area under the curve using calculus. We'll integrate horizontally, so we express x in terms of y, and use a horizontal strip from y equals 0 to y equals 2a by root 3. So the area of this bounded region becomes 20a squared by 9 root 3. Now that we've computed the area under the parabola for one symmetric slice of the region, it's time to bring it all together. Now remember, the full region R is made up of three such identical curved slices, thanks to the perfect symmetry of the equilateral triangle. We multiply it by 3, so the area of bounded region R is this. Next, we need the area of the entire equilateral triangle to compute the probability. Now we move to the final piece of the puzzle. Let's calculate the area of the equilateral triangle. But wait, before we can compute the area, we need to know the side length of the triangle. So what is the side length, in terms of a? Let's recall a key fact from the parabola. In the standard equation, y squared equals 4ax. The distance from the focus to the directrix is exactly 2a. In our setup, the centroid of the triangle acts as the focus, and each side of the triangle plays the role of a directrix. So the perpendicular distance from the centroid to any side is 2a. This idea will help us to find side length of equilateral triangle. Here is how. Now let's zoom into a smaller triangle within our equilateral triangle. The triangle GBM here. G is the centroid of the triangle, B is one of the vertices, and M is the midpoint of the opposite side. We're going to apply a little trigonometry to this right triangle. In triangle GBM, angle GBM is 30 degrees, a direct result of the 60 degrees angles in the equilateral triangle and its symmetry. Now apply the tangent ratio. Tan of 30 degrees is equal to 2a by bm, which implies to bm is equal to 2a root 3. Since BC is equal to twice of bm, therefore, BC is equal to 4a root 3. And now, the final step. We've determined that the side length of our equilateral triangle is 4a root 3. With this, calculating the area becomes a simple application of the standard formula. Area is equal root 3 into square of length of side by 4. Substitute the value of side. This gives us the total area of the triangle, clean and exact, which is 12a square into root 3. And now we can finally compute the probability. Area of required region by total area of equilateral triangle, which comes out to be 5 by 27. A perfect fraction. The elegant ending to a beautiful journey through parabola, symmetry, and integration. If you enjoyed this exploration, don't forget to like, share, and subscribe to the channel. We bring you elegant math, every step of the way, from curious problems to beautiful solutions. Hit the bell icon so you never miss a new drop, and let us know in the comments, what's your favorite geometric insight? Until next time, stay curious, stay sharp, and keep unlocking the beauty of mathematics.